let's start. And first of all, I would like to say a couple of words regarding this presentation. And it will be divided into two parts. The first part will be devoted to connection between apparent horizon and energy conditions, and we will consider the evaporation of black holes, especially regular black holes, and the results which I have obtained. They somehow contradict the usual picture of evaporation, black hole evaporation. So I think it sounds interesting, and I hope you will find it interesting. And the second part devoted to regular black hole formation. Mostly I was interested how we can obtain this regular black hole core, which is this core, from usual barotropic matter. Because if we consider usual massive star, which undergoes gravitational collapse, then some phase transition should happen there to form this exotic matter which supports the regular center. But inevitably, if we have phase transition, where one type of matter transforms to another type of matter, then we have energy flux. And we can actually estimate energy flux from this star, and as a result we can say what's the black hole will form in this case. Because as you know, when we consider shadows, when we consider quasi-normal modes, these things say nothing regarding the structure, inner structure of black hole, if it's regular black hole or singular black hole. So that's why we should look only at gravitational collapse, just to find out how to understand if regular center is formed. Okay, and let's start the first idea. First idea which I would like to explain is the following. When we consider a usual black hole, for example, just let's consider Schwarzschild, for example, and you all know this Bekenstein-Hawking formula, which states that the smaller the mass of black hole is, the hotter it is. Yeah, so supermassive black holes has negligible temperature, Hawking temperature. And when we have evaporation of black hole, then apparent horizon, because in dynamical case we don't speak regarding event horizon because it's defined globally and only in static case. We speak about marginally trapped surface, which is called apparent horizon, and this apparent horizon during evaporation of black hole is time-like hypersurface. It's shrinking. It's a usual picture which we all know. But let's consider the following situation. Most of black hole solution, especially when we speak regarding regular black hole, they possesses two horizons. For example, Reisner Nordstrom possesses two horizons, exterior one and inner one. Hayward spacetime, Dymnikova spacetime, Bardeen spacetime, the spacetime which we obtained with Ali last year, they all possesses only two apparent horizons. Only two apparent horizons. And we can actually state that usual regular black hole, asymptotically flat regular black hole, possesses two or even numbers of apparent horizon. It's necessary to make sure the regularity condition in the center. Otherwise, there is no any regularity in the center. So we must ask for even numbers of apparent horizons. And usual picture states the following thing. if we consider the evaporation process, then both horizons are time-like, hypersurface and the shrinking. However, let's consider simplest case, Reisner-Nordström. Reisner-Nordström, it's of course it's not really good a black hole solution from real astrophysical point of view, because we expect all black holes to be neutral ones. But anyway, it's helpful because it has, first of all, a simple form, and we can easily express its event horizon locations. So as I told you, there are two event horizons in Reisner-Nordström spacetime. The first one, which I denoted R+, is exterior event horizon, and inner one is Cauchy horizon, yes, or inner event horizon. I denoted it as R-. And you see that, for example, if Q is equal to 0, then inner one vanishes, but exterior one is equal to M, Schwarzschild case. Yeah, we obtain Schwarzschild case. And let's consider the simplest case when, of course, it's unphysical, but it's just, this example just help us to understand the picture, which I would like to explain. Just imagine the following situation. Mass of black hole starts to evaporate. So it means that, for example, we have that the total mass is a bit decreasing. Yes, so we consider m minus delta m, where delta m is an negligibly small quantity. And let's consider what's going on with horizons. The exterior horizon, as expected, it's shrinking. Yes, so it becomes smaller during the evaporation process. It is how we expected. Yes, so its behavior natural. But let's look at inner horizon. What's going on with inner horizon? If we reduce the mass of black hole, then inner apparent horizon starts growing. So it's his location is grows. So it doesn't shrink like in natural picture, like we are used to. So that's why I decided to consider what's going on with all these horizons during the evaporation process. Because, for example, black hole might evaporate not only because it loses mass. It can evaporate even if it gains mass. Yes, it sounds like absurd, because just evaporation means that it's shrinking. However, imagine the following situation. We consider the accretion of charged particles. Just charged particles. Every particle gives black hole its mass and its charge. Yes? But if we consider usual elementary particles, charged particles, then the ratio, dimensionless ratio of charge to mass is incredibly huge, like 10 to power 21 or 10 power 19 for protons, 10 to power 21 is for electrons. Yes, so charge is growing much faster than mass of black hole. Of course, we should consider powerful accretion, just to consider significant change in mass and charge. But anyway, charge starts growing faster than mass. Then what's going on? Because charge tends, in geometrized units, in centimeters, tends to mass value. It means that black hole during this process tends to extremal black hole. And as the result, when it will be overcharged, event horizon disappear, and we will have naked singularity in Dresden Northern spacetime. But this not what I want to tell you about today. I'm not interested in naked singularities, so let's consider regular black holes. Next, let's consider dynamical situation. Because to investigate the structure of apparent horizon, we must consider just these processes in dynamics. And the famous generalization of Reisner-Nordström solution is generalized by the charged by the spacetime of Bonner-Weider solution. You see, it's the same like Reisner-Nordström. The only difference is that mass and charge now are functions of time, so they changing with time. Okay, what's going on next? If we consider charged wider space-time, then we will realize, please pay attention to the formula which, to the quantity which I denoted R neg. Neg means, stands for null energy condition. So when we speak regarding charged wider spacetime, then it has region where null energy condition violates. So it doesn't violate only in the following picture, when, for example, Q dot less than 0. So we have charge evaporation process. So it's natural, and then this energy condition are valid in the whole spacetime. But anyway, in all other situations, we have violation. And I introduced a new notion. I called it null energy horizon, null energy condition horizon, or just energy condition horizon for short. What this notion means? This horizon shows what separates, this horizon separates regions where energy condition violates from the region where they are satisfied. Okay, so it's just null energy condition horizon. And my idea was the following, that the behavior of this apparent horizon somehow depends on this energy condition, depends on this null energy condition horizon. And let's dive into details. So let's consider the general case of black hole. So we have just a generalized wider spacetime as the exterior geometry. Mass function here depends on both time coordinate v and radial coordinate r. And we have three physical quantities which supports this solution. It's P and rho, it's pressure and energy density of usual matter, any matter which you want to consider, just introduce the equation of state. And mu is energy flux. And you see mu depends on dot m, where dot m, dot over dot means derivative with respect to time. So it means that if mass function is growing, then mu is positive. If it's decreasing, then mu is negative. And null energy condition states that mu must be greater than 0, greater or equal to 0. So it shouldn't be negative. But again, if we consider Reisner-Nordström spacetime, or just usual Schwarzschild spacetime, and consider the creation of charged particles, then we will realize that this null energy condition is easily violated. So it's not the big problem violates null energy condition. So mu depends on dot m. So it means dot m, when dot m is less than 0, we violate null energy condition. And let's go to the next. So it's apparent horizon, yes, title?
Yes.
Okay. So in generalized wider spacetime, the apparent horizon location in Eddington-Wittgenstein coordinates just defined by equation G00 is equal to 0. So we easily obtain that the apparent horizon location is R is equal to M. That's why we consider the following model. We consider the model that our black hole consists only two apparent horizons, only two. So we don't consider any other black hole solutions, just black holes with two horizons. Actually, I have a strong suspect that if we consider even numbers of horizons, the result will be the same, but of course it should be proven. So, okay, let's then consider the geometry on this apparent horizon. So, let's put this R plus, R minus into spacetime metric, into generalized wider spacetime, which is the first formula on this slide. So, okay, then we will have the following thing, that ds squared is equal to minus r dot dv squared plus r squared d omega squared. Yeah. The omega squared doesn't matter, actually we are not interested in it, we are interested in the first term, minus r plus minus dot dv squared. If r dot is positive, then it means that the apparent horizon is expanding and it's I'm sorry, it's not minus, it's just plus. R dot plus minus dv squared. So if r dot is positive, then it's expanding, and it means that this apparent horizon is space-like hypersurface. If it's decreasing, so it's shrinking, then it's time-like. So we expect the evaporation process to lead to shrinking apparent horizon, time-like apparent horizon. So it's a usual scenario. It's okay. And of course, we have a situation where r dot might be equal to 0. So it means that this surface r is equal to m is just null surface. Okay, then let's consider the following situation. Let's consider how this r plus r dot changing in time. So we take the derivative, because m depends on both v and r. Yeah, it's a complex function. We take apply just usual rule of differentiation, and we obtain the following thing: that r dot is equal to 2m dot divided by 1 minus 2m dash, 2m prime. And m dot and m prime is evaluated on r plus or r minus, depending on what evolution we are looking for. What we can say regarding the denominator of this expression. The denominator of this expression depends on horizon where we estimate this difference, 1 minus 2m dash, 2m prime. 2m prime must be always positive, because of course we want energy density to be positive or non-negative. Yeah, so it's always positive. And y minus 2m prime is positive when we consider outer apparent horizon, and it's negative when we consider inner apparent horizon. So we can just consider usual situation, and let 1 minus 2m prime on r plus greater than 0. It's well-known, established fact, even by Matt Visser. So I checked it. Yes, and 1 minus 2m prime on exterior apparent horizon is greater than 0. It's a well-known fact. and I just confirmed it. It's not my statement. However, then the apparent horizon evolution depends on this m dot. And if energy condition holds, then just look what's going on. If energy condition holds, then m dot is greater than 0, then r plus will be greater than 0, and it's expanding. So there are no any evaporation. It's okay, it's usual picture. But if r dot minus will be decreasing, it's time-lag, always time-lag, when energy condition is held. So in this case, we have usual scenario when energy condition is held, then exterior apparent horizon is expanding on time. Yes, it's a space like hypersurface. When it's when we consider inner apparent horizon, then it's shrinking. It's time like hypersurface. So when we consider enough time, then these inner horizons tends to singularity, and if we consider asymptotic behavior, the whole black hole should tend to wider space-time. It's inevitable. So let's then consider our neck. It's energy condition horizon. So in this case, energy condition horizon, if we consider, we have several situations. So the first situation when our neck is absent, I've just described. When we have space like exterior apparent horizon and time like inner apparent horizon, and wider space-time is asymptotic limit of this evolution. Okay, then let's imagine that at some point this null energy condition horizon appears inside the inner horizon and starts growing. What's going on? Just the first statement, which I can say as a theorem. So apparent horizon might be null surface if only if it coincides with energy condition horizon. So when these these horizons merges, then apparent horizon becomes null surface. So just imagine the situation. They merge, apparent horizon become null, and then it's located inside the inner null energy condition horizon. What's going on then? Then again, previous formula, m dot is negative for r minus, but m dot is positive for r plus. It means that both apparent horizons right now are space-like and they are expanding. So it happens when null energy condition violation horizon is located between two apparent horizons. What's going on next? Next, these energy condition horizons merges with exterior apparent horizon, and then exterior apparent horizons becomes null surface. After that, when both horizons are located inside the energy condition horizons, then again, please look at this formula. M dot is negative for both cases, yes? But still, 1 minus 2m prime is positive for exterior apparent horizon, but negative for inner apparent horizon. It means that, and this is the first argument which contradicts the usual picture. Apparent horizon exterior is time-like and shrinking, so we are right now in evaporation black hole process. But inner one, it's not time-like hypersurface anymore. It's space-like hypersurface, and it expanded. So these both apparent horizons tends to each other, and then they measure and disappear. So leaving horizonless object with regular center. So this we can consider like just some information logs paradox resolution, because we can say that in contradiction to Hayward prediction that when Hayward black hole evaporates, it leaves Minkowski spacetime. But this investigation shows, but if regular black hole evaporates, it will never leave Minkowski spacetime. It will always leave horizonless object with regular center. But the nature of this object, of course, should be investigated, should be understood. So let's consider this title, example 1, Josh, write down.
No, this is null energy condition, horizon evolution.
It's not interesting. Charge.
Yes.
Yes, example 1. So let's consider example 1. So example 1 is the simple. We just consider charge Bonner weighted spacetime and show explicitly that it depends, the evolution of apparent horizon depends on null energy condition horizon. So just take derivative of r plus minus with respect to time. Just do some simple algebra, and you will see the difference: r plus minus minus r neg. Yes, and you will see that r plus is space-like if it's inside inner end inside the null energy condition horizon, and vice versa. Yeah, so it's easy to show. Then let's consider Hayward spacetime evolution. So in Hayward spacetime, we can consider both situations. Initially, Hayward introduced this model as minimal model. It means that mass is the function of time v, but L is regularization constant. Is the constant, it doesn't depend on v. But anyway, we can consider the situation when it is also changing with time. But first example is simple. When we consider just mass evaporation, then null energy condition is violated in the whole spacetime. So in the whole spacetime it's violated. It means that both horizons tend to each other, and because it consists of two horizons, they measure and disappear. Of course, there is one very big problem here, because in this scenario, the extremal configuration will be reached at some finite value of time v. Just we will always find this time v when two apparent horizons measures. Unfortunately, for Eddington-Finkelstein spacetime, it's not really good coordinates, because it doesn't allows us to say nothing regarding physical time. So maybe v might be finite, but time coordinate t, yes, which we observe here, might be infinite. So might blow up. I don't know this, because the diagonalization of wide spacetime, it's really a hard task, and actually in general situation it can't be done actually. But okay, let's consider the situation when it's finite. Yeah. So anyway, we have two situations. If time coordinate t, just t, not v, it's finite, then we have horizonless object after disappearing of two horizons. If it's infinite, then the evaporation of black hole stops at black hole remnants. It's just near external black hole. So, and we can't say anything regarding complete evaporation in this case. Okay, here is just example when M and L are both functions of time. So, but it's actually behavior is the same. It's not much more interesting. And this is gravitational collapse. Yes.
Yes.
Could you tell me the title?
Gravitational collapse with interaction.
And this is model 1.
Yes.
Okay. So we can actually stop here for maybe some questions because I finished the first part. Or you prefer to ask a question after the seminar? What do you prefer?
We may continue.
Okay, let's continue. So, the following thing, which I started actually last year in April here in Cyprus, Vitalii, it's regular black hole formation. Last year, I considered the following thing. We just considered the star with usual radius, and we assumed the following thing, that on the surface of the star, the pressure is 0. So we have thus equation of state. And at the center, it's the Sitter curve. So we just have P is equal to minus rho. In this situation, the problem is that we considered the equation of state P is equal to K rho, where K is the function of R. So it's just barotropic-like equation of state. For simplicity, we put that it linearly dependent on R. We obtain new black hole, regular black hole solution. Yes, this paper has been accepted in CQG, but anyway, this paper says nothing regarding the formation of this exotic matter, how it can form. So, and my idea was the following. Actually, it comes from cosmology. You know, in cosmology, nowadays, models with interacting dark matter and dark energy becomes really popular. So we have the following situation in cosmology, where we have a total energy momentum tensor, which is conserved, but it consists of 4 parts, not 3 parts: radiation, matter, and dark energy. And we assume that radiation, energy momentum tensor, which is responsible for radiation, is conserved also. But energy momentum tensor, separate parts of, which are responsible for dark matter and dark energy, are not conserved. But the total, again, I repeat, the total energy momentum tensor is conserved anyway. So we have energy momentum tensor conservation. But it means that we have some energy flux from dark matter to dark energy or vice versa. Here I decided to consider the same thing. We have in regular black hole, in usual situation when we consider a black hole, we have continuity equation, which states r prime r, rho prime r plus 2p plus 2 rho is equal to 0. And I decided to consider the gravitational collapse, which consists of 2 parts. So it has 2 matter components. For simplicity, I just consider dust and radiation. And so this pressure, P, is the combination of P dust and P radiation. P dust is 0, so it's just P radiation. Yes? And rho is the combination of rho dust and rho radiation. So it's just the combination. And let's consider what's going on with the solution. Let's consider the first model, simplest one. When energy, I mean radiation and dust, doesn't exchange energy, with energy. So just total energy momentum tensor is conserved, but also conserved its separate parts which are responsible for dust and radiation. They are conserved. Okay, in this case we easily obtain solution of Einstein field equations, and no surprise that this solution leads to a singular black hole. We don't want it. Let's consider the following situation. Let's consider situation where we have dust and radiation, and they transforms to each other at the constant rate. So just this beta, it's the efficiency of transformations of dust to another type of matter with releasing energy as a form of electromagnetic radiation with energy density rho r. Yeah? So this this model leads to another type of matter. So now it's not dust anymore. So dust evaporates, just transforms to another type of matter, and releasing electromagnetic radiation during this process. But again, at the constant rate. So beta is constant. Again, we can easily solve this. Einstein field equation. We obtain results, which is a bit more difficult than previous one, than the previous model. But anyway, it always leads to singular black hole. It doesn't lead to regular black hole solution. So we can say anything regarding the situation when this type of energy exchange can lead to non-singular black hole. Then consider the following situation. When we consider gravitational collapse, then the star becomes denser, denser, and denser. And the denser star is, the more effective distance formation should be. Yes? So it means that this efficiency beta must depend on both r and v. Yeah, on time and radial coordinate. Moreover, we expect this efficiency grows to the center. So the denser star is, yes, the more efficiency is. So it means that b prime should be less than 0. It decreases. And of course, for this type of model, we can't easily integrate Einstein field equation just to obtain explicit result. But we can impose some restriction on beta under which we obtain a regular black hole solution. Of course, we can do this. Restriction, impose this restriction, and of course we can obtain a regular black hole solution. But anyway, it's just words. Let's consider explicit example. So if we consider beta as h divided by 3 minus ar, then the solution is the following, that we obtain regular black hole solution. So if efficiency behaves like this, we obtain regular black hole solution. The problem is the following here. Actually, we can find a lot of beta like this, and we can say anything regarding a real physical situation, unfortunately. So far, I can't explain this beta function. So yes, it's efficiency, but the form of this efficiency I can just express as the function of new matter parameters. So if we have just transition of baryonic matter to another type of matter with releasing energy as electromagnetic radiation, yes, then this beta can depend on this a new type of matter parameters and old matter parameters also, baryonic equation of state. But we should consider quantum physics effects, of course, just to realize if this beta is possible. Of course, some beta which is decreasing is possible. We can introduce, for example, when baryonic matter transforms to quark matter, and again we can obtain a regular black hole solution, just we showed to Vitalii last month. So it's okay. But let's consider what's going on then and how we can describe the process of gravitational collapse. And let's consider the simplest case. The title is Herzen.
Yes.
Let's consider Herzen solution. This solution corresponds to barotropic equation of state P is equal to alpha rho. But it's not barotropic equation of state, of course, it's just baryonically like equation of state, and because this P is anisotropic pressure. Actually, it's the tangential component of pressure. And of course, we should consider just average P is equal to alpha rho. Then we obtain barotropic equation of state. But actually, this equation of state will be nearly the same. You just change the constant alpha. So, for example, if alpha changes from 0 to unity here, for real barotropic equation of state, we have alpha changing from -1/3 to 2. It's okay, and so we obtain just baryonic equation of states. So the generalization is straightforward, and I won't repeat it. Herzen solution, of course, leads to singular black hole, only singular black hole. But we can consider the regularization process. Regularization process is the following. Let's consider the following situation. In Herzen solution, just pay attention to rho and P. Yes, when we consider alpha is bigger than 1/2, then when R turns to 0, pressure and energy density blow up. Just blow up, and we have singularity. So first of all, let's introduce new parameter beta. I'm sorry for confusing, but this beta parameter, it's not the same like beta from a previous model. It's just a parameter with length dimension. We just consider this beta because if we consider R is equal to 0, then we have energy density and pressure are constant there. Okay, if it's so, let's then solve Einstein field equation. To solve Einstein field equation, it's not easiest way, and we should consider three cases, but physically motivated cases are the following: when alpha is bigger than 1/2. In this case, you can obtain the result, which is extremely difficult, but when we do fine-tuning, then we obtain just a regular black hole solution, because we must ensure that mass function is equal to 0 when R goes to 0. Okay. Here, it's just, Ali, could you please tell me the title of this slide?
Regularization of Bonner-Wheeler.
Yes, regularization of point. Here, yes?
Yeah.
Regularization of Bonner-Wheeler. So here just an example how we can regularize this charged body space-time. Or if we don't consider dynamical case, just regularization of Reisner-Nordström solution. To be honest, I don't know if it has been done so far or not, because I didn't met this type of solution so far. So maybe it's the first solution of when we can regularize charged weighted spacetime. But anyway, you can ask me, what's this beta? How we have this barotropic equation of state? Then we have this strange matter with this beta. What's going on then? Okay, let's consider the gravitational collapse. Again, we consider the following situation. Let's call this solution, when we do regularization process. Yes, this rho and p, which corresponds to this new solution, let's call it new solution, and the matter which we have, we call new matter, just for short. So just imagine we consider a gravitational collapse of barotropic equation of state. Then, when the star becomes denser enough, then some phase transition to another type of matter should happen. So we consider the following situation. This barotropic matter transforms to this new matter, and as the result, there is some emission of electromagnetic waves, which we can detect actually if apparent horizons isn't formed so far during this process. Okay. And gravitational collapse we can describe by three regimes. The first regime, exterior solution, just usual collapse of baryonic matter. It collapses, but when it becomes denser, then it just starts to transform to another type of matter. So it means that baryonic matter just vanishes. And this layer between inside the star, it's just somewhere in the middle, yes, of collapsing star, where this process is happen. And during this process, all baryonic matter transforms to new type of matter and release some amount of energy. We can calculate this energy actually, and it depends of course on the process, it depends on the radius where it happens, and it depends on time, how much it lasts. Then we can estimate this energy flux, and this energy flux can be detected by external observer. To be honest, of course, some calculations should be done. I expect this amount of energy will coincide with energy of gamma ray burst. So it should be as powerful as GRB events. And the final, so there is some region near the center where the metric is described by new matter, just new matter, and it has regular black hole. So just again, we have three stages. The first stage, baryonic matter. Second stage, baryonic matter transforms to a new type of matter. Then when baryonic matter disappears, we have third stage, which forms the Sitter core, regular center. So these three stages of gravitational collapse can describe how usual matter transforms to exotic matter and what amount of energy is released during this process as electromagnetic radiation. So I think that's all what I wanted to tell you for today. Thank you very much.
Thank you very much, Vitalii, for visiting us and also give us this wonderful seminar. Yes, now we can continue with the equations.
So, whenever the null energy condition is violated, you call that exotic.
Not. Not exotic. Exotic, I mean, because just imagine, we consider usual thing, a creation of charged particles onto black hole. This process violates null energy condition because mass function is decreasing. It's not exotic. Under exotic matter, I mean the matter which forms the Sitter curve in regular black holes, because it always violates strong energy condition. It must violate strong energy condition in order to ensure that center will be regular. Otherwise, it will be singular always. It's just a theorem.
In Vitalii type things that if you forget the charge, you have just ingoing and outgoing dusts together. Then both possibilities are together. So I think you are only counting one phase, going out or coming in.
Yeah.
But this can be considered together, as that means the ratio, the time rate of the mass function can be both positive or negative. So in that case, I noticed in equation 50, the term that you obtain addition is exactly in electrostatic what is known as the